In this section, we will learn to program a microcontroller in assembly language. A microcontroller is a small computer on a single integrated circuit that consists of a processing core that handles the arithmetic and logical operations. It has built-in memory, both read-only memory and random access memory that allows you to store your program codes and variables. There are a set of input and output ports which are programmable. By this, I mean you can write instructions to either receive input on a particular pin or drive outputs from that pin. Interrupts are a means of providing signals from the outside world to the microcontroller to alert of certain events that are happening. So for instance, if you interfaced a keyboard to your microcontroller, then every time a keystroke is pressed, the interrupt signal is going to tell the microcontroller to leave everything it's doing, attend to the keystroke, and then resume operation once the keystrokes have been handled. There is a built-in analog to digital converter within the chip. So this allows you to convert analog signals from the outside world into a digital form before getting processed. The watchdog timer is a mechanism that allows the microcontroller to recover from programs which halt unexpectedly. So the idea here is that in the course of its operation, a program is periodically required to reset the watchdog timer, and in case if it does not happen because maybe the program has frozen, then what happens is a timeout occurs and the watchdog timer resets the microcontroller so that the execution of the instructions resume at the very first line of the program. The microcontroller is also capable of pulse width modulation. So this allows you to generate waveforms, let's say square pulses, and by controlling the on time with respect to the entire waveform, you can change the duty cycle of a wave, and this is useful in controlling certain devices like servo motors. So what makes a microcontroller special is that it has all these capabilities integrated within a single chip. And this is very different from a general purpose microprocessor that you find in your ordinary PCs. A general purpose microprocessor only has the processing core, and a general purpose microprocessor needs to then be interfaced with various memory modules and input and output peripherals. So for a relatively small price, you can get an integrated chip with all the built-in components in it, and this chip is programmable. And so given the cost factor, the ability to program, and number of features microcontrollers offer, they are really popular for embedded systems applications. So if you look around your house, you'll find microcontrollers being used in everyday devices like your dishwashers or washing machines. In fact, there's an instance of a internet-enabled toaster which has a microcontroller embedded in it. What this toaster does is checks the weather updates online, and in the morning when you're toasting your bread, it burns the weather update on your toast. We will be programming the 8051 microcontroller, which was introduced by Intel in 1981. Since its release, the microcontroller has gained wide popularity because Intel made the design available for the other manufacturers. So you'll find that manufacturers like Atmel, they have come up with their own integrated chips, and these flavors of 8051 controllers can vary in the speed, the clock cycle, or the amount of onboard memory it contains, but they are all code compliant with the original 8051 design. Let's look at the pinout for this controller. So VCC is where you will connect your voltage supply. Here's the ground pin to ground the controller. The reset pin allows you to reset the operations of the microcontroller so that it goes to the very first line of code in your program and starts execution from there. There are 4 ports on the 8051 controller labeled P0, P1, and P2, and these are their corresponding pinouts. Note all these ports are 8 bits wide. Some of these ports serve special function. So if you look at port 3, pins 0 and 1 are used for serial port communication. So RxD stands for inputs which are received at this port. TXD is the serial transmission pin. The other special pins on port 3 are the interrupt pins. So interrupt 0 and interrupt 1 are used to interrupt the microcontroller and provide alerts from the outside world for the microcontroller to respond to. You can hook up a crystal on these pins, and this allows you to control the timing operations within the microcontroller. Let's take a look at what's inside a 8051 microcontroller. So when you write a program in assembly language, it is first assembled and the machine code is stored in the read-only memory here. So that's where your program sits. There's a special register called the program counter, which points to the next instruction to be executed. So the way the microcontroller operates is that it fetches the instruction to be executed, and the instruction is placed in the instruction register where it is decoded. The actual execution of this particular instruction takes place at the arithmetic and logic unit, and the results of the operation is stored in a special register called the accumulator. For some operations like multiplication and division, a special register called the B register is also involved to store part of the results. The process status word is a flag register which shows the status of the execution of an operation. So sometimes if there is a carry bit or an overflow when you are doing addition, then the respective flag bits are set here. Your programs may use variables, and these variables are stored in the random access memory, which are addressable using registers called R0 to R7. Inside the 8051, there is no special memory allocated for stack. Instead, you'll find that you will be storing your stack on the primary memory here, and the stack pointer points to the item that is right on the top of the stack. This block here handles the interrupts, serial I/O, and timer, and it has been interfaced to the respective ports as shown. Finally, the data pointer is the other 16-bit register that allows you to access different regions of memory within the microcontroller. In a nutshell, the 8051 is an 8-bit microcontroller, which means the largest size of data it can manipulate at a time is limited to 8 bits. So if your data is larger than 8 bits, then what happens is it needs to be broken down into 8-bit chunks, and then operations can be carried out on that. The clock frequency is set to 12 megahertz, which times the execution of the instructions. So the instructions can take one clock cycle, or there are some instructions which just take 2 clock cycles to complete, and therefore at 12 megahertz clock frequency, the 8051 microcontroller can execute 1 million one-cycle instructions per second. The random access memory is where your variables and stack is stored. Typically you get around 128 bytes of storage space for that. The contents of your program is written in the read-only memory, generally stored on an elastically programmable ROM chip, which has a limited lifetime. Essentially, you get around 100,000 or so write and erase cycles. The nice thing about this is even when your microcontroller is powered down, the program does not get removed from memory. So when you power it back on, it starts executing the last program that was stored on this ROM. Through the input and output pins, you interface the microcontroller to the outside world. So the I/O can be digital in nature. So if it's digital, logic 0 can be indicated by pulling the pin to the ground and providing 0 volts. Logic 1 is generally indicated by supplying positive 5 volts to the pin. Sometimes the inputs from the outside world is analog signals, and for the microcontroller to process these signals, they need to be converted into digital. So here's an example of how this might happen. So a real signal between 0 to 3 volts can be enumerated using 8 bits as such. So when you receive 1.5 volts, the corresponding binary representation of this 1.5 volt is 127, which is essentially 0, 1, 1, 1. So the output of the microcontroller is rather limited, generally plus 5 volts with limited current supply, and this cannot drive heavy loads like if you want to turn off and on a machine. So normally you will find that the output of a microcontroller needs to be interfaced to a transistor or a relay in order to drive heavy loads. Let's take a look at an example of an application of pulse width modulation. So here is our microcontroller, and we can connect one of the output pins to the servo motor. A servo motor does not, you cannot drive a servo motor with just simple 1 or 0. You need to supply it with a constant pulse of square waves. And so by varying the duty cycle, that is the amount of time the pulse is on with respect to the rest of the waveform, we can control its direction of motion. So if this is the duty cycle, for this duty cycle, the servo motor moves counterclockwise. If you narrow down the duty cycle, then it starts rotating in the clockwise direction. If you want it to be keeping still at the center, then it's, in this case, it has to be exactly timed to 1.5 milliseconds. Here's an example of what an assembly language code looks like. So it starts off by equating the label count to this value 250. This is not the same as storing 250 in a variable called count. This equate is an assembler directive which tells the assembler that everywhere it finds the label count to replace it with the value 250. So in an essence, it does not take on extra storage. All it does is it makes your program more readable. Every instruction in assembler is written on a line by itself, and normally these lines are numbered. Instead of using numbers, we can use sensible labels to mark the specific lines of instruction. So this line here is labeled using the word tone. So what this instruction does is it clears the 7th pin of port number 3. So suppose this is our port 3.7 and this is the timeline. What it does is it sets the state of this pin to a 0. This line of code moves the value 250 into register R1. Note the direction of movement is always from the right side to the left side. So here is R1, our register R1, and now this has the value 250 in it. This line of code is marked by the label stay 0, and this instruction simply reads decrement the contents of R1 and jump to this line if the result is not equal to 0. So let's do that. It decrements this value, which now becomes 249, and since it is not equal to 0, it will jump back to this line which is stay 0. So what ends up happening is you are decrementing from 250 all the way to 0, at which point when it becomes 0, then the execution resumes and moves on to the next line. So what has happened here is we have executed this operation 250 times. For a microcontroller which has a 12 MHz clock, each cycle takes 1 microsecond, and this particular instruction requires 2 microseconds to complete. So therefore we have taken 2 microseconds for each instruction and it's repeated 250 times. We have now waited in this loop for 500 microseconds. So this is a simple delay operation which has caused the pin to stay at level 0 for 500 microseconds. After this, we set the 7th pin on port 3 to 1. So this becomes a 1, and so after 500 microseconds, switch to a 1. Next, we move the value 250 again into R1. So R1 becomes again 250. Stay 1 is the same instruction as stay 0. It allows the microcontroller to just simply decrement the contents of R1 250 times. Each time takes 2 microseconds, and therefore you end up waiting for 500 microseconds. At this stage, then it executes the next instruction which says short jump to this label here, which is tone. So the flow of execution of this program moves over to this line here marked by the label tone, and this clears the port 3.7. So basically for this 500 microseconds, this was set to 1, and then when we clear it, it goes back to being 0 again. So you'll find that this program runs in a loop, and all it's doing is generating a tone which is a square pulse which stays on 500 microseconds and stays off for the other 500 microseconds. And so the idea is if you were to connect a speaker to this pin on your microcontroller, you will get to hear a special tone.